Hi guys, Mrs. Valdivia here. So we're going to be going over the ideal gas law on our lab flow. So we're going to get started. Now I'm going to have you guys take some notes here with me so you know how to do the calculations because this is going to be very calculation based. Now when we go over the ideal gas law, there's a couple things that we must remember. And the first thing is the equation PV is equal to nRT. So let's go ahead and write that down. PV is equal to nRT. So this is the ideal gas law. And what we're going to be focusing and studying on is our R constant. How did we obtain that R constant uh, throughout, right, in the ideal gas law? So we're going to do that by obtaining the pressures, the volumes, knowing the number of moles and the temperature of a simple reaction. All right, so right here, what I have is my container with hydrochloric acid inside of it. And right here is my magnesium, right? And the magnesium is going to be reacting with the hydrochloric acid. Actually, it would invert, so it would go into the hydrochloric acid. And this is going to create some sort of gas evolution of hydrogen gas, right? So hydrogen gas is going to build up, let's use a different color here, right, into here. Okay. And it's going to go up to a certain amount. So this is our hydrogen gas. Okay. And that is in here. But we also know that outside of our system, so this is our system, and surrounding our system, right? Surrounding our system is our surroundings, okay? And our surroundings also has atmospheric pressure. And we're going to be taking into account that atmospheric pressure in order to solve our problems, right? Like, what is the R constant based on our atmospheric pressure, the amount of gas formed from hydrogen, and the actually atmospheric pressure of water as well. So all of these take into account. Uh, Here, as we scroll down, you're going to see that we have Charles, Boyle's, Avogadro's, and the combined gas law, and it tells us what are all the different constants, right? But all of these actually combine and give us an ideal equation known as PV equals nRT. Even though we could find everything individually, right, and we summarize them in this way, PV nRT is for our ideal gas. So we're saying this is going to behave ideally. The equation that we're going to be using in this reaction is going to be magnesium solid plus hydrochloric acid aqueous gives me magnesium chloride aqueous plus hydrogen gas. So we're going to develop some hydrogen gas. And you'll notice that this is going to be a single replacement reaction in which hydrogen ends up by itself. Okay. So what are a couple of things that we're going to have to obtain in here? When we do this lab, you're going to have to obtain pressures, volumes, number of moles, and the temperature of items. And we need to figure all of this out. Now, pressure is probably going to be the one that we're going to have to think about a little bit more because this is also going to involve atmospheric pressure. So for our pressure, we have to note that our pressure total is going to equal to the pressure of the water plus the pressure of our H2. Okay? And that's because atmospheric pressure is combined with water. So we have water inside our atmospheric pressure. When we take this into account, we have to be able to subtract, right? We're going to subtract our atmospheric pressure from our water pressure in order to obtain the pressure of hydrogen, to know what is the actual pressure of this. So to obtain the pressure of our hydrogen gas, we're going to take pressure of our atmosphere minus the pressure of our water. Okay. And I'm going to put that in absolute value, so you're not going to get a negative number that's going to form there, only a positive number, right? So just keep this in mind once we get to that section. And now in order to find the pressure of your water, that's all going to depend on what your temperature is. So our temperature is given to us in Celsius, and I'm pretty sure in the lab it's going to tell you what the temperature is. So make sure you know, okay, this is the temperature I was given. You're going to have to come back to your PDF for the lab, find that temperature, and then you're going to find the pressure of your water in Thor. And that's okay that it's in Thor because we're going to convert our Thor into atmospheres pretty soon. All right, with that being said, let's go ahead and start our lab. So now I'm going to be here on our lab, reset the attempt. Okay, we're going to do this lab virtually. Now right here is the instructions of how we're going to create this little masterpiece, right? Obtaining some magnesium ribbon that's going to be inside of here because we're going to react the magnesium with the hydrochloric acid. Now make sure that our magnesium doesn't have any rust on it, so you kind of sand it just slightly, okay? And then you're going to place it into this tube. Now when you place it into this tube, it's called an eudometer, and the eudometer is what's going to measure the gas that flows through it, okay? We're going to invert it into the hydrochloric acid solution. So once you place it in there, you invert it, and it's going to create a reaction, right? So the atmospheric pressure is going to start rising, and when the reaction happens, you're going to end up with hydrogen gas, and that hydrogen gas is what we're going to be measuring. So the first part is, how much magnesium are we using? And in my lab, it tells me I'm using 0.038 grams of magnesium. Next. Okay. And then it has a thermometer. So this is where we're going to read our thermometer readings. Okay. And mine has a reading of 21, 20, almost 22. So I would say 21.8 maybe degrees Celsius. All right. The eudometer reading. So look, now I have a couple things that are given to me. I have mass that's given to me, and I'm going to convert my mass into moles, which is going to be my N. Then I have the temperature. I have temperature, and it's going to be in degrees Celsius, and I'm going to convert that into Kelvin. And then I have my eudometer reading right here. So my eudometer reading is my volume. And my volume is in milliliters, and I am going to convert that into liters. Because if we look at this equation, we need atmospheres times liters. N is going to be my mole. And then T is going to be in Kelvin. And so far, we can have our moles, we have our Kelvin, and we have our volume. So the last thing that we would need to obtain is going to be our pressure value. All right, so let's go ahead and see what we have here. We have a 38.5 on mine. Oh, next. Oh, okay, so it says I need to be a little bit more exact, so 35.0. And the atmospheric pressure is 751. So pressure of the atmosphere is equal to 751 Thor. So I'm right, 751 Thor. Right, so this is information that we need in order to answer the rest of our questions that it's going to give us. Now we have to go through trial 2 in order to see the rest of our questions. Okay, so let's go ahead and go through trial 2. Actually, we don't need to do that. We have this open here. Okay, so we have all the information that we could possibly need, and we're going to do the math for our trials. Now, I'm going to do mine for trial 1, and then as easy as you guys can see this, you guys can start doing your own for trial 1 and for trial 2 as well. So mass of my magnesium ribbon, that was, I didn't write it down. I guess I do have to do this. Or no, here it is. So my mass was 0.038 grams. Whew. All right, that saved me. The temperature, I said, was 21.8 degrees Celsius. My milliliters is 38.5. milliliters. And my pressure was 751 Thor. So now I have all this information. The next thing it wants me to do is it wants me to obtain my vapor pressure of water. So we're going to go back up to our PDF. Okay. And in this chart, it says vapor pressure of water using the various temperatures. I'm going to look at my temperature. My temperature was 21.8 degrees Celsius. So 21.8, temperature 21, 22. I'm going to round that up to 22 degrees. So it's approximately 22 degrees. Okay. And I'm going to say that my pressure of my water is going to be 19.8 Thor. 19.8 Thor. So all I had to do was look at the temperature that I wrote down, go back to my chart, and then obtain my pressure for my water. Scroll back down. All right. So all of this information, nicely filled, no math needed to be done in any of this. Now we could go ahead and do some data analysis. So we're going to do some data analysis. So the temperature of H2 gas in Kelvin. So this is all my data. I'm going to get a new sheet of paper. I'll put my data aside so I could look at it. And we're going to start solving some problems. Actually, I need this right in front of me. So the first part, it wants the temperature of H2 gas in Kelvin. So it wants temperature of our hydrogen gas in Kelvin. Now, if we recall, in order to do this, Kelvin is equal to degrees Celsius plus 273.15. Kelvin is equal to degrees Celsius plus 273.5. I'm going to grab my fancy dancy calculator because I like having a calculator. Can you guys believe, like, back then when they didn't have calculators, people were so smart they could do all of this math in their head, but then we didn't have all these electronics that kind of gave us that short-term memory or anything like that, and distracted us from actually learning. So there was no distractions then, and now there's tons of distractions, and it makes it hard for us to actually learn. Cell phones, internet was actually like a big killer of our abilities to get deep knowledge and focus on content and become one of those like super geniuses. At least in my opinion. All right, so we have 273.15 plus 21.8, and I get 294.95 Kelvin. So this is going to be my K value, and I'm going to just circle that so I don't lose track of it. All right, question number 2, the volume of gas of H2 gas in liters. Okay. So quite simple. In order to do this problem, we're going to take our milliliters that is given to us, whatever number that we have, and we're just going to use a simple conversion factor, right? In 1 liter, there is 1,000 milliliters, and that's it. So the milliliters that I had, if I look at my data, I had 38.5 milliliters. So I'm going to take my 38.5 milliliters, and I'm going to use my conversion factor to solve this. Now, while I do my conversion factor, milliliters cancels out with milliliters. And this is just going to be 1,000 times smaller. So I'm going to move the decimal over, the understood decimal over 3 times. 1, 2, 3. And I should get 0.0385 milliliters. Question number 3, moles of H2 into gas. So now we're going to do moles of hydrogen gas. So we're going to convert grams to moles. So this is a simple stoichiometric problem. And in order to do this, we're going to take the number of grams. Actually, does it say moles? Yeah, moles of H2. So we're going to do moles of the grams of our hydrogen. How many grams of our hydrogen was used? Okay. I don't know why I was having a moment of this. We're actually going to do, like I said, simple stoichiometry, but it's a little bit more than just that. So we're doing grams of magnesium because we don't have the grams of our H2. We had the milliliters of our H2. We're going to do grams of magnesium to moles of magnesium to moles of H2. So we're going to do this in a couple of different steps. So I'll rewrite this, and this is going to look like this. So we're going to take our whatever value we got of grams of magnesium, and then we're going to take this into a couple steps. So the first step is we want moles of magnesium, and that means grams of magnesium is going to go on the bottom. And remember, this unit that you have here, bring it down. And when you bring it down, you're able to see that this unit goes on the bottom. And we're going to convert moles of magnesium into moles of hydrogen. So I want moles of hydrogen on top. And I want to get rid of moles of magnesium. So remember, take this unit here and bring it down. Moles of magnesium here. And that should solve our problem. Okay, now where do we get all of this information? Remember, grams to moles is the molar mass. And that comes from the periodic table. Mole to mole ratios, those are the coefficients from the balanced chemical equation. So I'm going to write balanced equation. And this right here, this is what we measured. Measured mass. Let's go ahead and get this ball rolling then. So the grams of magnesium used, I used 0.038 grams. Now I'm going to convert, and I'm going to rewrite this. Now the grams of magnesium, like I said, comes directly from the periodic table, and that's going to be 24.31. And then the next step is going to be my mole to mole ratio based on that balanced chemical equation. And if you guys remember, the balanced chemical equation, we wrote it down. There is 1 mole of magnesium. Remember, if there's no number in there, it's just a 1. 2 moles of hydrochloric, but we're not using that. 1 mole of magnesium chloride, and 1 mole of hydrogen gas. So the moles of hydrogen gas, we said was 1, and the moles of magnesium was also 1. So it was just a 1:1 ratio. Grams of magnesium cancel out with grams of magnesium. Moles of magnesium cancels out with moles of magnesium, and I'm left with mole of hydrogen gas, which is exactly what I wanted. So I'm going to obtain my handy dandy calculator, and I'm going to 0.038 divided by 24.31, and that gives me 1.56 to the negative third. 1.56 times 10 to the negative third moles of hydrogen gas. So now I have found my N. The next step, pressure of hydrogen gas in atmosphere. So if you guys recall, right here earlier, we said that the pressure total is equal to the pressure of the hydrogen plus the pressure of our hydrogen gas. So therefore, the pressure of our hydrogen gas is going to be the pressure of our atmosphere, the total pressure of our atmosphere, minus the pressure of our water. Let's go ahead and write all these little steps now. Okay, so we have pressure total is equal to pressure of water minus pressure of the hydrogen gas. So therefore, the pressure of, by the way, these 3 dots doesn't mean my crazy life, all right? It actually means therefore. So pressure of hydrogen is going to equal to the pressure of the atmosphere minus the pressure of the water. And then this is going to be in Thor. So then we have to convert this Thor into atmosphere. So we're going to take whatever we have here and we're going to add a step to it. And that step is going to be to convert it into atmosphere. So we would take this and then we'd say, all right, in 1 atmosphere, which is what we want, there is 760 Thor. So step 1 and step 2. Let's go ahead and solve. So the pressure of our atmosphere was given to us as 751 Thor. So I got 751 Thor. So whatever you got, make sure you use your number. Minus the pressure of my water. And I looked that up, remember? So that was based on the temperature. And I just went up to the little chart on top of the PDF and we just looked it up, right? My temperature said that the pressure of water is about 19.8 Thor. So I'll do that. And then once I'm done with that, the last step is to divide it by 760 Thor. So here we are, 751 minus 19.8 gives me 731 and 31.2 Thor. Now, like I said, the next step is just 1 atmosphere over 760 Thor. We could easily see now how the units of Thor are going to cancel out. So Thor cancels out with Thor, and I am left with a unit of atmosphere, which is what I want. So I'm going to take my answer and divide it by 760. And that gives me 0.9621. And I'm just going to write atmospheres. So in all, we have obtained the following. We've obtained our T. We have obtained our V, the N, and the P. And we need all of those in order to calculate PV equals nRT and find what our R constant is going to be. So now let's find our experimental R constant. PV is equal to nRT, we are going to be solving for R. Therefore, R is equal to PV divided by NT. Let's go ahead and solve for our R. Our pressure that we solved for was 0.962 atmospheres. Our volume was 0.0385 liters. I wrote this wrong. So actually, let's go back over here and fix this. So I did the calculation correctly, but I wrote the unit wrong. So this is liters, not milliliters. And I'm going to circle that. Okay, liters. And I'm going to divide this by my mole value, which is 1.56 to the negative third mole. And my temperature of 294.95 Kelvin. Let's go ahead and solve this using our fancy dancy calculator. 0.962 times 0.0385 equals to that, divided by 1.56 to the negative 3 is equal to that, divided by 294.95. So our R value came out to 0.0805. I'm going to just round that to 0.5. And the units are atmosphere, liters, over mole, Kelvin. All right, so quite simple, all these little steps, especially after they get explained. If you keep track of all your work, remember, keep track of all your work, and you're going to be submitting that work onto your report value. So the last two questions say, what's the average value of your R? And average values are easily obtained. So what's that number going to be? This is going to be pressure. Let's just say average value of R here. Is going to be your R1 from experiment number 1 plus your R2 from experiment number 2. And you're going to divide that by 2. And that's going to equal to your average R value. The next question says percent error. So it wants to know, what is your percent error? And percent error is found with this equation here. So percent error is equal to the absolute value of the actual value that you obtained minus the theoretical value divided by the theoretical value times 100. And that's going to give us your percent error. Now your theoretical value, that's your R value that we kind of look up. What is our R constant? It should be listed up here. If not, you guys should know it from our gas laws. It's like 0.081, I believe. See if we find it here. Oh, here it is. So this is our theoretical value. And let's go ahead and write that down. So the theoretical value of R is going to be 0.08206, and the unit is liters atmosphere over mole Kelvin. So this is your theoretical value. All right, you guys, I hope this lab was useful and you guys are able to score 100% on it. All right, you guys, take care. Ciao.